Okay, so we now have this free body diagram. So this is the 30 kilonewton external load, this 50 kilonewton external load. And for the reactions, we have this 30 kilonewton load acting to the left, 10 kilonewton load acting upwards, and 40 kilonewton load acting upwards. So they are AH, AV, and RC respectively. So now that we have our reactions, let us now solve for the bar forces. So we have proved earlier that this truss is a statically determinate truss. So meaning by statically determinate, once again, that we can actually solve for the bar forces of this particular truss using using the equations of static equilibrium. So we can actually make use of a method of joints, so method of joints, or method of sections. But we have a catch here. So suppose that we would be we would be making use of method of sections here, or method of joints, I should say. So let us now use method of joints here. So let's say at joint A. So if I am now to draw its free body diagram at that particular joint. So we have here your 10 kilonewton load upwards. So we also have this 30 kilonewton load to the left. And for the bar forces, we have AD, we have AE, and we also have B, call this AB. So again, these are AD, we also have AE, then we also have AB. And we also have here your 30 kilonewton load and your 10 kilonewton load. Okay, so from that, using method of joints, what you would be doing is that you would just be getting the equations here. So summation of forces vertical. So for the summation of forces vertical, this should be equal to 0. So what are the vertical forces here? So we have AD, which is upwards. Then AE, since it is slanted, we must get its component or its vertical component. So for the meantime, let us now refer to it as AE, Y, its Y component. Then AB does not have any vertical component, so that is to be it for these two unknowns. For these three unknowns. And also acting vertically on that joint is this 10 kilonewton load. So plus 10 kilonewtons. So this is now equal to 0. Since we still have one equation and then we have two unknowns, we must write another equation to satisfy the two equation and two unknown requirement. So with that, let us now formulate our second equation. So the summation of forces horizontal, this must be equal to 0. So what are the horizontal forces here? So we have this negative 30. So negative 30 kilonewtons. Then plus AB. So plus AB. Then what else? So since once again A is slanted, let us get its horizontal component. And that is AEX. So plus AEX. So this is now equal to 0. And with that, this is now our equation number 2. So looking at these two equations, we actually have 1, 2, and 3 unknowns. So we have 3 unknowns here. So meaning we cannot solve for anything yet. Because once again, in order for you to solve for 2 unknowns, you must have 2 equations. And since we have 3 unknowns here, we must also have 3 equations. So the next thing that you will be doing is that you will be going to the other joints. So go to the other joints here at these parts and formulate another equation. But the thing is, oh, I'm sorry. So I think this drawing is erroneous. So we do not have a bar member there, if I'm not mistaken. So, okay. So this is, this is what it should look like. Okay, so proceeding once again. So this is what happened when we have solved for this particular joint here. So what if we are now to check for this joint here? So for this joint here, so same story, we still have 3 unknowns. And for this particular joint here, we have 3 unknowns. And for this joint here, we have three unknowns. Well, actually, for all of the joints, we would be having three unknowns. I mean, three unknowns apiece. Unlike before in method of joints, so suppose that you will be getting this particular joint here. So solving for this and solving for this, so we only have two equations and two unknowns, so we can solve for both. And once that you will proceed here, this is already known. So with that, the only unknown forces here are these values and these values. And since we can formulate two equations in that particular joint and we only have two unknowns, meaning that we can actually solve for this. And proceeding here at this part, we now have these two, which is known actually. So we only have two unknowns. So unlike in our problem right now here, we cannot solve for anything yet because we do not have a joint that only has two unknowns. Actually, all of the joints here have more than two unknowns. So I would just be erasing this part because this part is quite unnecessary for our method for today. But just so you know, so with that, for the first joint, so for joint A, you can formulate two equations. So let us name them as equation 1 and equation 2. Then for joint B, let us name them as equation number 3, equation number 4. So for joint C, we have equation number 5, equation number 6. For joint D, we have equation number 7 and equation number 8 up until joint D or G, I should say. So up until the last joint G, whereas we can now derive. So how many equations do we have? So we have 14 equations. So let's say that for joint G, you can formulate equation number 13 and equation number 14. So using all of these equations, you can actually solve for all of the bar forces by making use of advanced algebra or numerical solutions to civil engineering problems such as matrices, Gaussian elimination, Gauss-Jordan. So if you have mastered those procedures, then you can just derive all of the equations and then, solve for it via Gauss-Jordan, Gaussian elimination, whichever you like. But the thing is, I do not want to make use of those methods because that is quite lengthy. So what I will be doing now, or what I will show you right now, is another procedure, which is actually in the title already. And that procedure is what you would be calling substitution method. So the advantage of substitution method as compared with making use of matrices is that, of course, in making use of this procedure, it is solely dependent upon your advanced algebra skills and in your skills in numerical solution. So that is one approach. So the other approach is by making use of the method of substitution. Okay, so I will be erasing this already. So method of substitution. Okay, so again, in order for you to make use of method of joints effectively, you must have at least one joint with a maximum of two unknowns. And as you can see, all of the joints does not have two unknowns or below three unknowns. Okay, so with that, for method of substitution, what we would be doing here is that we will be rearranging one member in such a way that we will now have a certain joint that only has one unknown. So in Tagalog or in Filipino, ang gagawin lang po natin, yung isang member dyan, ililipat natin para yung isang joint, dadalawa lang yung mismong magiging unknowns niya. Okay, so let us try that here. Okay, so with that, maybe I want to move my member BB. So let's say that I want to move this. So what I will do is that I will remove that there. and maybe assign another truss member, maybe right here. So earlier we have a member DB, but for that particular member, I have removed it and I have placed it here. So with that, guys, this particular joint is already free from the third member. So if we would now apply method of joints here, we can now solve for member DG and member DA or AD. And from that, since we already know the value of DG, upon solving for joint G, we can now solve for member GE and member GF since DG is already known. And the domino effect will now go through or will now take into effect, and we can now solve for everything. However, if you would be wondering, wouldn't the result be different since we do not have this particular truss or this original truss member here any longer and we have placed it here? So you are actually correct. But since we have removed here, what we must do is for us to place an arbitrary unit load here. So since we have removed this particular member here, let us now place a unit load here. So let us now place a unit load which is in tension here. So let us now name it as 1 kilonewton, or let us now assign 1 kilonewton to each of these nodes. So in method of substitution, you will be required to memorize another formula, which is actually very easy to memorize. Whereas S, so let's say that S is now your bar force, S is now equal to S1 plus S2x. So this is now your, this is now the new equation that you will memorize. So this S here is the actual bar force. And S1 is now equal to the bar force, which is transformed. So when I say transformed, meaning, for a moment. So when I say transformed, it means that from the original figure like this, you have already transformed it in such a way that you can now solve for it. So we have transformed it by removing this truss and moving it at this manner. Okay, so from that, S1 is now the bar force of each of these members due to load only. So due to load. So meaning that we will now disregard this unit weight here, or unit load I should say here, and just solve for the bar forces. Then S2 right now, so S2 is now the bar force, of course, transformed. So when I say transformed here, it means that our basis is this figure and not this figure. Okay, so proceeding. So bar force due to unit weight, unit load again. So unit load only. Okay, so from that, our first goal is for us to solve for S1. So I have created this table here, whereas this is our actual bar force later on. So this is now the bar force due to the load, and this is now the bar force due to the unit load. So right now, I will be solving for this one here. So proceeding here, or getting back to these figures, I will just be copying this to our next slide. So with that, let us now solve for S sub 1. So for S sub 1, let us just remove this unit load here. And let us now analyze this truss. Oops, sorry. So let us now analyze this truss, making use of method of joints. So since we have already freed this particular joint of its third unknown, let us now get the bar forces at this particular joint. So with that, at joint D, so getting the summation of forces, let's say horizontal equal to 0. So for that joint D, What are the horizontal forces there? So we have 30 kilonewton load. So positive 30 kilonewton since it is going to the right. By the way, my sign convention is to the right positive. So what else do we have? So we have the bar forces of DG and DA. So you have DG and DA. And since we still do not know their bar forces, let us assume that it is tension. So by tension meaning that it is pointed away from the node. So DG is pointed at this location and the A is now pointed at this location. So for that, this is now equal to, so 30 kilonewtons. What else? What other horizontal force do we have? So we have this DG here, but we must get its X component first. So plus DGX. So this indicates X component. So do we still have other horizontal forces? So not any longer. So this is now equal to 0. Okay, so solving for DGX. So DGX is basically the X component of this bar force DG right here. So in order for us to get the X component, we must have, of course, the slope. So since this is 2 meters and this is also 2 meters, then the slope there is 1:1. Or maybe you can also refer to it as 2:2. So same thing, 1:1 is also equal to 2:2 is also equal to 3:3, 4:4, and etc. So with that, we must get the hypotenuse of 2:2. So the hypotenuse of that particular truss or that particular slope is now equal to the square root of 2 squared plus 2 squared, or the square root of 4 plus 4, square root of 8, that is 2 square root of 2. So that is now 2 square root of 2. Okay, so with that, guys, for DGX, if this is now the force triangle or the triangle, and let's say that this is now DG, and this has a slope of 2, 2, and square root of 2. In order for you to get the X component by trigonometry, so DG times what is the X component of this slope? So the X component of that slope is also 2, so 2. And just divided by the hypotenuse. So the hypotenuse is 2 square root of 2. So from that, guys, so substituting it here, so 30 kilonewtons plus dg times 2 over 2 square root of 2 is equal to 0. Okay, so before I solve for this, so let me explain this further. Okay, so suppose that this is now your triangle, or this is now your angle. This is now your bar force DG. So bar force DG has its own horizontal component and also its vertical component. So let's say that this is now DGX and this is now DGY. So in this case, what I am solving for here is DGX. So for DGX, how can you solve for DGX? So suppose that we have a certain angle here, or angle theta here. So from your trigonometry, SOHCAHTOA. So in order for you to solve for this, since DGX is adjacent with your theta, it means that you will be making use of this. Because in SOHCAHTOA, ka means cosine, adjacent, and then hypotenuse. So meaning, if this is now the angle, and this is now the adjacent side, and this is now the hypotenuse, you can actually say cosine theta is equal to adjacent, which is DGX in this matter, and DG. So DG is now, DG is now our hypotenuse. Okay, so with that, in order for you to solve for DGX, so DGX cross multiplying would give you an equation of DG cosine theta. So there. But what about for the angle of theta? So since this one here, also has the same slope. So the slope here is 2, 2, 2, and 2 square root of 2. So making use of the same rule or SOHCAHTOA, so for cosine theta is also equal to, so adjacent divided by hypotenuse. So if this is now our slope, the adjacent side of this particular angle here is 2. And its hypotenuse is 2 square root of 2. Take note, guys, that this triangle here, or the big triangle, has the same angle here. So this angle is the same as with this angle. So there, okay, since this angle is the same as this angle, we can actually substitute this cosine theta here to this equation. So with that, dgx is now equal to dg. And what is the value of cosine theta? So cosine theta is also equal to 2 divided by square root of 2. So 2 divided by 2 square root of 2. So that is where 2 square root of 2 came from. So coincidentally, if you would be getting the y component, it is still 2 square root of 2 because the vertical component here is also 2. But for pretend that, let's say, you have a slope of 4, then 3, and if you would be getting the hypotenuse here, this is now equal to 5. So to prove you're right, so 3 squared plus 5 squared, so that is now equal to, 4 squared, I should say. So that is now equal to 25. So the square root of 25 is equal to 5. So there. Okay, so suppose that you will be getting the x component using this slope. So let's say that you have the value of vector A. So let's say AD. For example, you are solving for this. If you would be solving for its y component, then the y component here is 3/5. So y, 3/5. Then for its x component is 4 over 5. Since 4 is the horizontal, so this is now the x, this is the horizontal, and y, or the vertical, is 3. So 3, 3, 4, and 4. So that is just the basics from statics of rigid bodies. So going back here, so we can now solve for the value for dg. So solving for the value of dg, so that is now equal to, so negative 30 times 2 square root of 2 divided by 2. So our answer here is negative 42.426 kilonewtons. Okay, so negative 42.426. So with this, I will now write our answer here for bar force due to the load. So once again, that is for dg, and that is negative 42.426. Okay, so we can actually solve for another here. So using the same joint, which is this particular joint, we can still solve for member AD. So member AD, so same thing. There is nothing new here. So this is just a matter of method of joints. So guys, again, there should be nothing new here at this particular method. This is just method of joints. So I am just solving for the bar forces using this particular setup. So we can also solve for dA or AD by getting the summation of forces vertical equal to 0. Okay, so what are the vertical forces acting at joint D? So we have this force going downwards, and that is dA or AD. So it will now be equal to negative. So let me just draw if you are getting confused at this particular figure. So again, we have a 30 kilonewton load here. Then we also have dg So this is DG, and this is now AD. So DG and AD. So we have 30 here. Then we have DG here. And we have AD here. So since we have already solved for the value of DG, which is a negative value, meaning that it is now, meaning that we have assumed the wrong direction. So since I have initially guessed or assumed tension, since it is negative, this should actually be tension. So this is now the correct figure, or this now its correct way or direction. So this now equal to 42.426 kilonewtons. Okay, so solving for the value of AD via summation of forces vertical. So with that, so let us solve for AD. So for AD, that is now equal to negative AD. So it is negative since it is going downwards. So by the way, this is now our sign convention. As for DG, so we must get the y component of this. So minus, since this is pointing downwards, so it means that it is, well, downwards, negative. So negative 42.426 kilonewtons. But take note that our concern here is not 42.426. Rather, our concern here is its vertical component. So for its vertical component, so what is the slope once again? So that is 2 square root of 2. So we must multiply this by 2 divided by 2 square root of 2. So where did this come from? So in this particular slope, once again, 2 square root of 2. So just multiply it by the vertical one here and divide it by the hypotenuse. So it's like a matter of ratio in proportion if you do not really like to hear the term trigonometry, but this is actually from trigonometry. So this is now equal to 0. Then solving for AD. So AD, solving for AD, so you can either use shift solve or any. So this now equal to, so if I am to transpose negative AD to the other side and solve for this particular value, so our answer here is now equal to negative 42.426 kilonewtons times 2 divided by square root of 5. Square root of 2, I should say. So our answer here is negative 30 kilonewtons. So that is for AD. So in here, I will be listing it here, negative 30 kilonewtons. Okay, so from that, you will now follow the same procedure. So since you already know this value and this value, it is of your best interest if you would now go to this or this joint. So if you would be going to this joint, since you already know this value, you can now solve for the bar force here and the bar force here. Or if you would now be going to this joint, you can now solve for the bar force here and the bar force here. So what you would be doing is that you would be solving for all of the bar forces, including this new truss member here, and list them here. So you would be listing them here. Okay, so let us have another example here before I skip. So let's say that we would now be going to joint A. So for joint A, what are the forces acting about joint A? So let's say that this is now joint A. So we also have a 30 kilonewton load here, a 10 kilonewton load here. Then we have the bar force AB. We also have the bar force, what is this? AE. Then for AD, we have already solved for it, which is negative 30, meaning that it is compression. So compression means that the force is towards the joint always. So this is now 30 kilonewtons. Then this is now 30 kilonewtons also. This is 10 kilonewtons. Then we have the values of A AB, and AE. So for this, you can get the summation of forces vertical equal to 0, upwards positive, in order for you to solve for AE. So what are the vertical forces here? So we have this 30 kilonewtons acting downwards, so that is negative 30 kilonewtons. Then this 10 kilonewtons acting upwards, so plus 10 kilonewtons. Then AE, since AE is pointing upwards, so that must be positive. AE, so what is its vertical component? So multiply it once again by the vertical side of the slope, which is this particular value here. So the vertical side. Then divide it once again by the hypotenuse. So this is now equal to 0. So with that, AE is now equal to, so looking at the calculator to your left, so that is now equal to 30 minus 10. Or better yet, if I would just be transposing them here first. So 30 minus 10, of course, that this would become positive and this would become negative. Then you will now be multiplying this by, well, by cross multiplication, 2, square root of 2 divided by 2. Okay, so from that, AE is now equal to, 2 times square root of 2 times 30 minus 10, and that is 20 divided by 2. So our answer here is now equal to 28. So AE is now equal to 28.284 kilonewtons. So again, I will now be listing them here. So that is, what was that once again? AE. So AE is equal to 28.284 kilonewtons. Okay, so there is nothing new in the next procedures. So in order for you to fill all of this up, so you will now go, you will now make use method of joints. So you will now make use of method of joints to all of these joints. And you can now actually solve for all of this already. So if you have already solved for all of this, this is now the bar forces due to the load. Okay, so after solving for all of the bar forces due to the load, the next thing is for you to solve for the bar force due to the unit load. So if you can remember from earlier that in this particular figure, so I will copy it once again here. So we have introduced a unit load. So we have introduced a unit load in place. So in place of the original truss member. So once again, originally we had a truss member here, which we removed and which we placed at this particular portion. And to take into account that we have removed it there, and to take into account that there is actually a presence here, or there is actually a bar force here, we are assuming that there is a tension load here, 1 kilonewton. So with that, for the next side of the table, or the next part of the table, you will now solve for the bar force as if that this is the only load. So with that, we will now remove all of the loads, including the supports. So we will now be removing all of them here. And just solve for the bar force. So there. So we will now solve for all of the bar force using this particular unit loads. Okay, so if you are wondering why did I remove the reaction? Because if you would now solve for the support reactions here, so suppose that there is still a roller here, or a hinge I should say, and there is a roller at the other part. If you would now be getting the summation of forces vertical, both of this would just simply cancel themselves out. So the summation of forces vertical is equal to 0, summation of forces horizontal is equal to 0. You would still have an answer of AH, AV, and RC, all of them equal to 0. So there, AH, AV, and RC would all be equal to 0 if you only have this unit loads here. Okay, so with that, we will now go with method of joints once again, starting at this point. So at joint D once again. So at joint D, let us now solve for the bar forces. So we have here um, DG. So this is DG. This is AD. So DG. This is AD. And this is the 1 kilonewton unit load. So this is now the 1 kilonewton unit load. Okay, so let us solve for this too. So getting the summation of forces horizontal equal to 0. Once again, the slope here is 2, 2, and 2 square root of 2. So what are the horizontal forces here? So we have the horizontal component of dg and the horizontal component of 1 kilonewton. And 1 kilonewton here also has a slope of 2 to 2 square root of 2. So with that, dg, so to the right positive, so dg is positive. And then multiply this by the horizontal component of the slope, 2, and divide this by the hypotenuse, so 2 square root of 2. Okay, so next, you also have 1. Since it is to the right, so plus 1 times 2 divided by 2 square root of 2 once again. So this is now equal to 0. Then solving for dg, dg is now equal to negative 1. So negative 1. So meaning that I have assumed the wrong direction, meaning that the correct arrow head should be located here. Okay, so from that, I will now proceed to the summation of forces vertical equal to 0, upwards positive. So we have here dg. So dg. So for the vertical component of dg, that is dg times the vertical component of the slope divided by the hypotenuse. So times 2 divided by 2 square root of 2. So there. So what else? So we have a downward force here. Oh, by the way, this is also downwards. Since this is now the new, what you call this? This is now the new direction. So negative dg times 2 divided by 2 square root of 2. So minus AD. So do we still have vertical forces here? So we still have the vertical component of 1 kilonewtons here. And since it is pointing downwards, this must also be negative. So negative 1 kilonewton times, so we are getting the vertical component of this. So times the vertical side or the vertical component of the slope, which is 2. Divide this by the hypotenuse of the slope, which is 2 square root of 2. So this is now equal to 0. So substituting the value of dg to this one here, so this is now equal to negative 1 times 2 divided by 2 square root of 2 minus AD minus 1 kilonewton times 2 divided by 2 square root of 2 is equal to 0. So I probably know what you are thinking right now. So I think you think that I am committing an error here because dg is equal to negative 1 and I have only substituted 1 here. So if you are wondering or if you are thinking that it should be negative 1 times 2 over 2 square root of 2 dot 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 dot, then you are wrong because this is erroneous and this is actually correct. Okay, so this negative symbol here only denotes that you have assumed the wrong direction. So WAD. Okay, so from that, since we have already corrected it, so initially I have assumed that this force is tension, and since I have assumed wrong, I have just reversed this one here. So I have already reversed its direction. So the 1 kilonewton load is pointing downwards. And there, in this negative symbol here, that indicates that it is now downwards. So if you would still be substituting this to this equation, then there is already a redundancy. Once again, I have already indicated this negative symbol right here, which indicates downwards, and the magnitude of dg is 1. So meaning that this is still 1 kilonewton, but it is now pointing downwards. Okay, so proceeding, so once again, this is wrong. So solving for the value of AD will give us an answer of, so transposing this to the other side. So AD is now equal to, so negative 1 times 2 divided by 2 square root of 2. So take note guys that this is identical. So this one is identical with this one. So with that, I would just be multiplying this by 2. So this is now equal to negative 1.414. So with that, I would now be writing them here. So we have for DG, which is negative 1. So DG, that is negative 1. So I have inputted them here. Then for AD, that is negative 1.414. So where is AD? Here. So that is negative. Oops, is this negative for a moment? Yes, this should be negative. So negative 1.414. So you would be listing them all once again. So the next thing that you will do after getting this bar force here is for you to get this bar force here, get this bar force here, here, and all of the bar forces. And once again, upon solving for all of the bar forces, you will now list them here. Okay, so what is the next procedure that we will do? Okay, so once again, the actual bar force S is equal to S1 plus S2X. So why S2X? So S2X, so S2 is just a unit load. So we need to multiply it by a scale factor X for us to have an accurate answer. Because S2 in here, we have just assumed a 1 kilonewton load. But the thing is, that is not really 1 kilonewton, but we do not know that yet. We can actually refer to this value of X here as, let's say, a factor. Because once again, S2 is only an assumption of a unit load. And this X here will now take into consideration the actual bar force. So he will scale, or the value of X will now scale the value of S2 in order for it to be accurate. Okay, so how can we solve for the bar force? So making use of this equation for the actual bar force, just add the value of S1 by the value of S2 times X. But what is X in the first place? So how can we solve for X? So we still do not know the value of X. So take note that for member BE, so where was that? So this member here does not really exist in real life. So with that, guys, so as you can see, there is no member BE here. So meaning that since this is fictitious, so once again, it is fictitious. So for member BE, the actual bar force here is actually equal to 0. So from that, guys, so since that is 0, we can actually solve for the value of X in this row right here. So from that, since S is equal to S1 plus S2 times X, so S is equal to 0, S1 is equal to 20, and S2 is equal to negative 1.414 times X. So solving for X, that is now equal to 20 divided by 1.414. So proceeding, so X is now equal to, looking at the calculator, so 20 divided by 1.414. So the value of X is now equal to 14.1443. So this is now the value of X. Okay, so from that, I will just store this. So shift store to X. So the value of X is true for all of the members. So for all of the members, the value of X is equal to 14.1443. So for the actual bar force here, so do I have a list? So no. So for the actual bar force here, what you will be doing is that for DG, so let's say DG. So for bar force DG, that is now equal to negative 42.427, which is this, minus 1 times the value of x, and the value of x is equal to 14.1443. So as a shortcut, I will just input in my calculator alpha a plus alpha b times x. However, for alpha x, so I have already stored this to alpha x. So once again, alpha a plus alpha b times alpha x. So I will be pressing calculator, so calc here. So upon pressing calculator here, the calculator would ask me what is now the value of a. So the value of a is negative 42.427, and the value of b is negative 1. So the value of x remains the same, which is 14.144, so equal sign. So my bar force here is now equal to negative 56.57 or 571 kilonewtons. So a negative value represents wrong assumed direction, since I have assumed that for all of my trusses, positive would be for tension and compression would be negative. So with that, I will be assuming negative here. So with that, guys, meaning that this answer here is compression. So for all of my negative answers here, they are compression, and for all of the positive answers here would be for tension. So for the second row, or for GF, so I will be pressing calc once again. So this is now equal to negative. So negative 42.426. So negative 42.426 and negative 1. So same answer. So 56.5702. So negative 56.57 kilonewtons. Then for GE, okay, so proceeding, I will press calc once again. So the calculator would ask me what is the value of A. So the value of A is 60. So that is now equal to 60. And the value of B is equal to 1.414. So 1.414. So the value of X remains the same. So the answer here is now equal to positive 80 kilonewtons. Okay, so upon completing all of this, our answer should be this ones here. So we have 56.57, 56.57, 80. So for the next, that should be negative 50. So let us prove it. So what is the value here? So that is now equal to negative 30. So I would be clicking calc, then type negative 30, then type negative 1.414. So negative 1.414. Sorry. So negative 1.414. So that is now negative 50. Okay, so this is now our answer if you have already completed it. And take note that for my methodology here, all of the positive values are tension and all of the negative values are under compression. So this would be true. So this would be true if in your method of joints, so if you would be making use of method of joints, if you still do not know the bar force, always assume to be positive. So meaning, so suppose that you have a certain joint. If you still do not know the bar force of this member here, always assume tension. When we say tension, it must be away from the joint. So if your joint is here and your bar force is here, always make sure that the arrowhead is pointing away from the joint. Okay, so in making use of this method requires understanding in method of joints. Okay, so that is for today's video. I'm sorry if it is quite fast. So if there are any questions, feel free to message me.